We're going to continue with how to draw curved arrows. In the beginning, I recommend that you always label your nucleophile and electrophile so that your arrows point in the correct direction. The arrowhead should point at the electrophile. Do you need a review of what a nucleophile and electrophile are? A nucleophile is a pi bond lone pair or negative charge. An electrophile is a positive charge, partial positive charge, or incomplete octet. The group 3 atoms are the atoms with the incomplete octet. Let's look at drawing our arrows. Drawing arrows from the pi bond, because the pi bond is our nucleophile, to the electrophile, hydrogen. As I said, let's just go ahead and label that. Nuke. E plus, electrophile. How could we make an arrow with this? You could draw the arrow from the carbon to the hydrogen. This would be incorrect. Carbon is not giving electrons to the hydrogen. The pi electrons are moving to the hydrogen. Carbon does not have a lone pair. Carbon does not have electrons on it that you can show moving. You must draw the arrow from the electrons to their destination. Reaction coordinate diagrams. I've already reviewed this with you once, but let's look at this again. The y-axis is free energy, or delta G. The x-axis is the progress of the reaction. The beginning of the curve is the free energy of the reactants. The maximum is the transition state, the highest point on the reaction pathway. That is the transition state. And then the end point of the graph is the free energy of the products. Reaction coordinate diagrams show energy changes that take place in each step of the reaction. We're going to talk briefly about thermodynamics, how much product is formed, and kinetics, how fast is the product formed. Equilibrium constant gives the relative concentration of reactants to products. Remember that equilibrium is products divided by reactants. If KEQ is greater than 1, products are favored. If KEQ is less than 1, reactants are favored. Exergonic and endergonic reactions. Delta G is the free energy of products minus the free energy of reactants. If the free energy of the reactants is greater than the free energy of the products, then delta G will be negative and the reaction is exergonic. When KEQ is greater than 1, an exergonic reaction, delta G is negative. So those are two characteristics of delta G for exergonic reactions. Delta G is negative and KEQ is greater than 1. Products are favored. So delta G is less than 0. It's negative, it's less than 0. And KEQ is greater than 1. Products are favored and the reaction is endergonic. Exergonic. Exergonic. Energy exits. These are the reactions that become warm to the touch, such as the dissolution of sodium hydroxide into water. Remember that the process of dissolving a salt is favorable and tends to result in a negative delta G, releasing of heat. This is true for graph A. Let's look at graph B. In graph B, delta G is positive. This means that delta G is greater than 0 and that KEQ is less than 0, or is less than 1. And the product and the reactants are favored. We can calculate this relationship using the equation free energy is equal to -1 times the Arrhenius gas constant R, temperature in Kelvin, and the equilibrium and the natural log of the equilibrium constant. This is an equation that you should remember from Gen Chem, but it is not an equation that we are going to use in this course. We use this equation to derive the general value of delta G when KEQ is 1, greater than 1, or less than 1. But mostly, in this course, we are going to use reaction energy diagrams to describe the progress of the reaction. We are not going to use mathematics to describe the progress of the reaction. Delta G is equal to negative delta H minus T delta S. This is an equation that we will use in this course. These are all delta G naught, delta H naught, and delta S naught are what we call state functions. Only the change in the value is relevant. So the pathway by which we achieve delta G, delta H, or delta S is irrelevant. Only the change in energy, the change in enthalpy, or the change in entropy has any significance. They are state functions. We are going to use these equations to determine the mostly delta G using free energy of products minus free energy of reactants to find delta G. And I believe that this is also on your homework. Another way to state this, free energy of products minus free energy of reactants, the one that we are usually use is bonds broken minus bonds formed. And we're going to cover that in a slide or two or more. I don't know how many slides until we get there. Okay, so delta G gives free energy. Delta H, remember that that is enthalpy, the heat term. Spelling. L-B-Y. Okay, and S is entropy, the amount of order in the system. And one of the laws of thermodynamics says that We are always moving towards greater entropy, greater disorder. Okay. We will use Lachaise principle a little to control organic reactions in the lab. So you need to be familiar with Lachaise principle and how a system will adjust if you make changes to it. Lachaise principle: if an equilibrium is disturbed, the system will adjust to offset the disturbance. If I add A, more C and D are made. If I remove D, more C and D will be made. If I add D, more A and B will be made. Coupled reactions. In an organic reaction, followed by a coupled reaction is an endergonic reaction followed by an exergonic reaction. This term is most applicable in biochemistry. We do use this also in organic chemistry, and I will point out if we see any reaction diagrams where coupled reactions occur. If we couple an endergonic reaction to an exergonic reaction, then the overall energy of the reaction from A to C should be exergonic, so that the step from A to B may require energy, but the amount of energy achieved as you move from B to C exceeds the amount of energy needed for moving from A to B. Calculating delta H. Okay. Delta H, we're going to say bonds broken minus bonds formed. So what bonds are being broken when we take ethene, react it with HBr to make bromoethane? Notice that in the product, there are no pi bonds. The pi bond breaks. Notice that in the product, there is no bond between bromine and hydrogen. The H to Br sigma bond breaks. Those are my bonds broken. What bonds are formed? In the reactants, carbon 1, in the reactants, the yellow carbon has only 2 bonds. In the products, the yellow carbon has 3 bonds. There is a new carbon to hydrogen bond. New C to H sigma. Notice that in the reactants, there is no bond from carbon to bromine. And in the products, we have a carbon to bromine bond at the orange carbon. New carbon to bromine sigma. We have a chart that gives us the enthalpy of pi bonds, of H to Br sigma bonds, of carbon to hydrogen sigma bonds, and of carbon to bromine sigma bonds. You will use this chart to determine the enthalpy of reaction for the conversion of ethene to bromoethane. The pi bond of ethene, D stands for the triangle delta, the delta enthalpy of ethene for a pi bond is 62 kilocalories per mole. This is essentially the same as a homework problem that you will be doing. So when you get to the math problem on your homework, you might want to refer back to this slide. The hydrogen to bromine bond, the delta H of this bond is 88 kilocalories per mole. The total energy of bonds broken is 150 kilocalories per mole. Remember, we're going to take bonds broken minus bonds formed. That's the total energy of bonds broken, not just one at a time. If you write them out one at a time, you have to distribute the negative or the subtraction to all terms for the bonds broken. I recommend figuring out the total energy of bonds formed and the total energy of bonds broken, and then plugging them into the final equation, bonds broken minus bonds formed. For bonds formed, the carbon to hydrogen bond is 101 kilocalories per mole. Formation of the carbon to bromine bond, the enthalpy is 71 kilocalories per mole. The total energy for bonds formed is 172 kilocalories per mole. We take 150 and we subtract 172, and we achieve a delta H of negative 22 kilocalories per mole for this reaction to occur, and that is the enthalpy of reaction. Here is the chart that you will use in your homework to determine bonds broken minus bonds formed. Let's find the values that we use. The chart does not contain pi bonds. The homework problem specifically tells you what the value of pi bond is that you should use. Be looking for that when you read the question. Many students have accidentally read the question and not seen the value for the pi bond that it states. It's easy to ignore numbers when they're in parentheses. Sometimes our eyes just don't see them. The HBr bond. Where can we find the HBr bond? Let's highlight it when we find it. Here we go. HBr sigma bond 87.5 kilocalories per mole. They rounded this to 88. In your homework, they probably would not allow you to round unless one of the numbers does not have any decimals. Remember your sig figs. Mastering is very particular about sig figs. Now let's look for the other values. C to H. Where is our C to H? We're looking for the value 101 kilocalories. Our carbon to hydrogen bond for a carbon that is bonded to another carbon is 101 kilocalories, shown at the highlight. This is the value for a carbon that has one bond to carbon and other bonds to hydrogen. The value of the enthalpy of the bond to the hydrogen at the terminal carbon is 101.1. The carbon to bromine bond. The carbon to bromine bond should be in this last section. Here it is. Or more accurately, we should pick the carbon to bromine bond for the carbon that also has a bond to carbon. 70.5. Again, they used 70.1 rounding up. In your homework, they probably would not let you round up. So we found the values in the table. You can see the table has many values. Be careful to identify the correct value.